Curvilinear coordinate systems 10, a tokamak fusion device has a geometry that takes the shape of a donut or torus. Calculations for such a device are sometimes done with the toroidal coordinates shown in the figure below. R, theta, and phi are the toroidal coordinates. The major axis of the device is a vertical straight line that forms the toroidal axis of symmetry. This is our major axis. The minor axis is a circle of fixed radius capital R0 that passes through the center of the donut. That's this circle. The position of a point is described by the coordinates r, theta, and phi. The coordinates r and theta are similar to a two-dimensional polar system aligned perpendicular to the minor axis. The coordinate phi measures the angular position along the minor axis. Now we're going to do part E. Write expressions for the gradient, divergence, and curl operations in this system. Because we already obtained the scale factors in part C, we can do this. Now the gradient operator is qi hat divided by hi del del qi. So basically we have to write the unit vectors er hat divided by the scale factor hr del del r. This is our gradient operator, plus e theta hat, our unit vector, divided by the scale factor h theta del del theta. And then we have e phi hat divided by the scale factor h phi del del phi. So this is what we need to do to obtain the gradient operator. So substituting what we have for the scale factor hr, we found in part C hr is equal to 1. So this is simply er hat del del r. And for e theta hat, we have the scale factor h theta, which is r. So we have 1 over r del del theta. And the scale factor we obtained for phi was r cosine theta. So we have plus e phi hat 1 over r cosine theta del del phi. This is our gradient operator. Now the divergence is obtained by 1 over the product of the scale factors. So that is hr, h theta, h phi, 1 over r square cosine theta. Then we have to take a derivative with respect to r of h theta h phi ar, which means r square cosine theta ar. And then we have the partial derivative with respect to theta hr h phi, which is r cosine theta a phi theta. And then we have partial derivative with respect to phi hr h theta, which is r a phi. This will give us the divergence of vector A. Now you can see here the r derivative doesn't affect the theta part, so cosine theta comes out. Therefore, we obtain 1 over r square del del r square ar plus, now we have the theta derivative that doesn't affect r, so we have to cancel this r and this r for this term. So we're going to obtain 1 over r cosine theta del theta cosine theta a theta. And then we have the phi derivative. R is not affected by the phi derivative, so similar to the previous term, we have 1 over r cosine theta del phi a phi. So this gives us the divergence operation in this coordinate system. Now, as for the curl operation, we have to take the determinant of ER hat del R HRAR. So this is going to be equal to AR, and it's also HRER hat. H theta E theta hat, which is R E theta hat, del theta, H theta A theta, which is R A theta. Then we have H phi E phi hat, R cosine theta E phi hat, del phi, R cosine theta A phi. And we have to divide this by the product of the scale factors HR, H theta, H phi, which is 1 over R square cosine theta. And we can do this with respect to the first row here. Now for the first term, let me do this upstairs. For the first term in ER hat, parentheses, I'm going to have, I have to cross out the first row and first column, del theta of R cosine theta A phi minus del phi of R A theta. So we have del theta of R cosine theta A phi minus del phi of R A theta. This is for the ER hat. And now for R E theta hat, we have del phi AR minus del R cosine theta A theta because of the minus sign. So we have plus R E theta hat del AR del phi minus del R cosine theta A phi. And as for the last term here, we have del R A theta minus del theta of AR. So plus R cosine theta E phi hat del R of R A theta minus del AR del theta. Now, I'm going to divide this by r square cosine theta, and I will also pay attention to to each of these terms here. So it's best to basically keep it as it is and say, because for example for this term I could write this as, because the theta derivative doesn't affect r comes out 1 over r cosine theta del theta cosine theta a phi, etc. So I can express my answer by saying this is the determinant, and I have to multiply it by 1 over r square cosine theta. So this is one way to write our answer for curl of A. If we want to be more specific, as I said, we can work on each of these terms. So let's do that here. This is also equal to, for the ER hat term, the first term I had was a theta derivative. So I had del theta of r cosine theta a phi. R is not affected. So I'm going to obtain 1 over r cosine theta, because it was r square cosine theta, now it becomes 1 over r cosine theta, del theta of cosine theta a phi. This is the first term. And then the second term was a phi derivative of r a theta. Again, r is not affected, so I could say it is also equal to minus 1 over r cosine theta. The derivative with respect to phi of a theta. Now I realize that I could just write this in 1 over r cosine theta parentheses. So let's do that. So this is all multiplied by 1 over r cosine theta. That's for the ER hat term. For the next term, I had r e theta hat, which means I really have 1 over r cosine theta. So this is going to give me 1 over r cosine theta e theta hat. And let's work on the parentheses. Del AR del phi. This is not affected. The next term is minus the r derivative of r cosine theta a phi, which means cosine theta is not affected. So let me take the cosine theta out. Cosine theta r derivative of r a phi. But I also have a cosine theta here. So then I realized that I could write it this way. So this first term has 1 over r cosine theta. So it's e theta hat 1 over r cosine theta del AR del phi But because I already have a cosine theta here, this is going to be 1 over r del del r of r a phi. This is the e theta hat term. And for the e phi hat term, I had an r cosine theta e phi hat. So r square cosine theta becomes just r. So it's 1 over r e phi hat. And then I have an r derivative del del r of r a theta minus del ar del theta. So after these simplifications, basically, this is my final answer for curl of A written in toroidal coordinates. All right. So let's review what we did here. For the gradient operation, we have qi hat over hi del del qi, which means we have to write the unit vectors in the new coordinate system, divide them by the scale factors, and take derivatives with respect to the individual coordinates. So er hat over hr del del r, hr is 1. E theta hat over h theta is r. E phi hat over h phi is r cosine theta. So that's what I substitute here. This gives me the gradient. Divergence is 1 over hr h theta h phi, which is r squared cosine theta. Del del r h theta h phi ar del del theta hr h phi a theta, and del del phi hr h theta a phi. So this was hr h phi a theta. This is hr h theta a phi. So here I realize that the r derivative doesn't affect cosine theta, so I obtain 1 over r squared instead of r squared cosine theta. Here I have a theta derivative, r is not affected, so I have prefactor 1 over r cosine theta, and phi derivative doesn't affect r, so I have a prefactor 1 over r cosine theta for this term. For the curl operation, I have to write 1 over product of the scale factors determinant hr hat, h theta e theta hat, h phi e phi hat, del del r del del theta del del phi, hr ar, h theta a theta, h phi a phi. So I substitute these here and do this determinant with respect to the first row. I have del del theta of this minus del del phi of this multiplied by er hat. For this one, I have del del phi of ar minus del del r of r cosine theta a phi. I changed the order because of the minus sign. And for this term, I have r cosine theta a phi hat times del del r a theta del del theta ar, all multiplied by 1 over the product of the scale factors. And then I considered the derivatives that are not affecting the prefactors in each term, and simplify the answer simplifies to this final form.